Now let's continue with 3.2 examples. So question number 7 talks about write the negation of each of the statement. All triangles had 3 sides. So this is a for all, and of course the predicate will be that it has 3 sides. So if we're going to negate this, we'll go with there is this or some triangle has more or less than 3 sides. This is just one way of negating this. Of course, you can also say some triangles does not have 3 sides, which is much more simple. No bird can swim. You can rewrite this first as all birds cannot swim. All birds cannot swim. This is equivalent to this. Okay? So the negation of this will be some birds can swim. Now, in C, we have the opposite. We have some rectangles are not squares. So if we're negating this, we will say all rectangles are squares. D is if a number is divisible by D, then it's divisible by 5. Okay, so we're assuming this is universally quantified over the integers, of course. So if we're going to negate this, we'll say there is a number or there is an integer divisible by 10 and not divisible by 5. Notice that that and happens because we're negating an implication. Okay, this and occurs because we're negating, here we have a P implies Q, so if we're negating that, we do P and not Q. Now for 8, we have, consider this statement, all differentiable functions are continuous. So we want to write this statement using quantifiers. And this is a true statement from calculus. So we can write this with a couple of predicates. We can use d of f, being f is differentiable. And we can use c of f is continuous. Okay, so if we do that, we can write this as for all f that belongs to, let's say, the domain of the functions, then differentiable implies continuous. If we're going to write this in the negation form, the symbolic form, we will say that this is f that belongs to the functions, so that is differentiable and is not continuous. We'll use the negation here instead of just writing something more specific. Now, writing the negation in English will be assist a function differentiable and not continuous. So is the negation true or false? Well, because this is a true statement from calculus, all differentiable functions are continuous. Of course, the negation will be false. Now let's move to question 9. In question 9 here, we're checking once again for a statement that they can be necessary or sufficient. So we're just going to check those. So being a square is a condition for being a rectangle. And of course, this is a sufficient condition. I'm going to just SUFF for sufficient. And I'm just going to write S by sufficient, and I'm just going to write N by necessary. So this is a sufficient condition. Notice that a square is indeed a rectangle, so it is just enough. Now, being a rectangle is a condition, is a necessary condition for being in a square. Notice that you first can talk about being a rectangle, and then you can check if it's a square or not. So being by the order of implication, of course, being a rectangle is something that you need to check first before getting to being a square. Now, being divisible by 4 is a condition for being even. And so, of course, this is a sufficient condition because if it's divisible by 4, then it's 4 times something, which can be seen as twice times something. So it's just going to be a sufficient condition. Being even is a condition for being divisible by 4. Well, this is the opposite. So in this case, we will have that this is a necessary condition. Okay? All right, so question 10. Once again, we're back to writing negation of quantifiers. We have for all n that belongs to the integers, if n is prime, then n is odd or n is equals to. So the difference here is that we're not only have an implication, but we have an or in bold. So we have this is for all n that belongs to C in symbolic form. F is prime, so P of n is going to be prime. Then, and I'm just going to call this odd of n, or, and I'm going to call this S of n. This is different predicates. S of n will be n is equals to, of n will be n is odd, and P of n will be is prime. Now, if we're going to simplify this by using Morgan's law, if applicable, then we can just rewrite this in a different way. But of course, we want to use this to maybe consider the negation, because we're doing Morgan's law. Okay, so if we want to write here the negation in clear English. So the way that we do that here is that it's going to assist in n that belongs to C, such that n is prime, which is our first thing, and n is even, and n different from 2. Notice that this will be the negation of this by Morgan's law. This is an assist and that belongs to C, so that P of n and negation of O n and negation of S of n. This will be what happened by Morgan's law. And so the final negation in English for this is there's an integer not prime, there's an integer prime since we still have that is prime, even and different from 2. Which is a false statement, by the way, but still. Now let's go with question 11. True or false, and we'll play the reasoning. The negation of for all x of P of x is for all f negation of P of x. This is false. And of course, is we're not negating the for all quantifier. Okay. Then the negation of assist x p of x is assist x minus negation of p of x. Once again, this is false, and we're not negating the assist x. To disprove for all x p of x, you need to find one counterexample, and this is true. To negate a for all, you just need one example that makes it false. To disprove an assist, you need to find one counterexample. This will be false, because to negate an assist, you need to find all cases. You need to prove all cases. Okay? All right. Let's go to question number 12. We have every student who studies hard will pass the course. So we want to represent this in symbolic form. And we have the statement S of x is a student, and h of x studies hard, and p of x passes the course. So we can write this here for all x, so that S of x, right, who studies hard, or let me just write this here differently, so it's a little bit more simpler. So for all x, so that S of x in h of x, we have that as a student is studying hard. Then for all x, that S of x in h of x, then p of x. So we have the n here. Now, if we're going to write this negation in symbolic form, this is going to transform to an assist x. Because this is an implication, we don't negate the initial stuff. So we're going to have S of x in h of x, and then now in negation of p of x. Okay? So this will means that this is a student is going to study hard and he won't pass the class. So this is a student who studies hard and will not pass the class. This was this symbolically mean. Student studies hard and will not pass the class. Which one is easier to prove, the original statement or the negation? Well, it will be easier to show the negation because it's an excess. And for the assist, only need one case. Okay? Now, question 13. Let's write a negation of there is a number greater than 1,000. So if there is, their assist is an assist, so we're actually going to negate this with a for all or every to make it simpler here. So we'll say every perfect number is less than 100,000. Okay? Also, you can write this as a perfect number. All perfect number are less or equal than 100,000. Okay. Now, question 14. For all x that belongs to R, if x is different from 0, then x squared is bigger than 0. And we want to negate this. So if we negate this, and notice this is a P implies Q situation. So simple enough, we do assist x that belongs to R, so that x is different from 0 and x squared is less or equal than 0. That will be the negation. Is the original statement true? Yeah, the original statement is true. So that will mean that the negation is false. In particular, there's not going to be a non-zero real number whose square is not positive. Okay? Here, the original is true, so the negation will be, by example, false. Okay, so this concludes the examples for section 3.2.